Hey everybody, thanks for coming this morning for day two. I just wanted to kick things off with just a welcome, and I sent out, or there was a revised day two agenda, so you get an idea of what we're going to dive into for today. We did, for the sake of time, since we got a little bit delayed yesterday, we did remove a couple sections, notably mesh adaptivity, a discussion of mesh adaptivity, and a discussion of interface kernels, which is a system for connecting two different media, as it's been used in our plasma research, actually, anyway. So those are still in the slides, so they're still available as a reference if you want to know more about that. And if you have questions about any of that, if you want to look through it, just please feel free to let any of us know or post to the user group.
And if there's an interest in having me setting a tutorial up for any of those sessions, we can also try to arrange that.
Yeah.
And through YouTube or something.
Yeah.
If you prefer a lecture type format for that material, we can try to set that up. But just drop us a line on the Google groups and let us know if that's something you'd be interested in having
Yeah.
added to the online content.
Yeah, and so again, as Steve was saying, all of this is what has been done so far is on YouTube, or is being streamed to YouTube and will be saved to YouTube. So if you wanted to look back on any particular section, then that'll be available to you. So anyway, so we're going to get things kicked off with. Are there any questions, burning questions that anybody had from yesterday? That maybe we can quickly.
Where's everyone at with it being installed, being able to follow along with the interactive parts? Everyone's been able to
At least get to a point where they're happy with it anyway?
everyone's been able to run?
Okay, great. All right, well, if there's no questions right now, we'll go ahead and dive into coupling, and Corey's going to get us started with that. So thank you.
We saw a little bit of coupling in the last section when we talked about fluid equations. So let's head right into it. So in this case, we're going to show coupling between variables. In particular, we're also going to introduce auxiliary kernels and auxiliary variables. And then we're going to actually couple and find electric field for that. So coupling, multi-phase coupling. Okay, so coupling variables, you can do this to any kernel. All you have to do is you have to set the params, add couple variable. The variable is still any variable, so you can set first order Lagrangian. That's by default. So in the kernel, when you set the kernel, what you have to do is give the kernel a name, the variable that the kernel is acting on, and then the coupled variable. Note that this name right here is the name you decided to put in your kernel, and this name right here is whatever the name of the variable you put in your input file is. Kernel. It's always the same. Just like the U variable, any couple variables also have many options. You can just do the couple variable. Variable old is the variable from the previous time step. Older is the variable from the DOT of the variable. So basically anything you could do with the variable you're acting on, you can also do with coupled variables. These functions, classes, yep. Also very important variable too. So let's say you have a Poisson's equation. So you have your voltage, which is the variable of the kernel. And then you have your electron density and your ion density, which are your two different coupled variables. When you do your Jacobian, you're going to have three separate Jacobians. One when you take the derivative with respect of a voltage, one for the ion density, and the other for the electron density. So just like regular variables, you can set something a little bit special. We saw this yesterday. With a couple variables, what you can do is you can set a initial variable such that if you just don't designate your couple variable, it will automatically set to 300 in this case. Number file, the proper size, continues the default value. Yeah, exactly. I said this is the default value. Additionally, you may also want to use so in the input file, which we'll get to soon, if you want to do debugging, and you just want to set your variable to a constant, you can do that inside the. If you think something's wrong with your Poisson's equation, but you already coupled electron density and ion density in there, you can set those to constants and run your Poisson's equation and see if you get the solution you expect for those two constant densities. Basis function of our previous steps. Oh, functions, sorry. I thought I was just still talking about a couple variables. Yes, functions. Functions are very important. So apply that voltage as a sine function. What you can do is you can have a Dirichlet boundary condition, in particular a function Dirichlet boundary condition. So your variable would be your voltage. Your function, you designate another object. I think it's in the next page. We'll get to it. But yeah, you would designate in another block, and you would type out your function. But so when you do a function voltage, when you create a function, you still have you can make a custom function that operates on a variable and also the gradient of the variable. So anything you can add to a kernel, you can inherit from a function. Yeah, just as I was mentioning before, functions are mostly commonly used for boundary condition initial conditions. So say you have you know that your initial voltage is some profile. You can set up functions that are already inside Moose is your function Dirichlet boundary condition. So it's just your normal boundary Dirichlet condition, but with a function. Neumann initial function initial condition, and user force function. Parameters, yeah, all the each of these types has a function parameter which is set in the input file and controls which function object is used. So similar to coupled variables, when you want to apply a function to your boundary condition or your initial condition or your boundary conditions, you will need to add in your parameters, put your function name. This would be the name of your function. This is the default. Also, if you can also do same thing, but instead of an initial variable, you can just do an initial function. And we can see here, it's taking whatever time step, or whatever time we're at, multiplied by the sine of our y dimension, or wherever we're at in our y space. A partial function, a constant function object is automatically constructed based on the default values right here, if the function name is not supplied in the input file. Okay, so here's some actual code that we can look at. So here's a function block. You can declare which one's active or which one's, if you don't want to use one, you can just not declare it in your action. This is one of the default functions, so you're just setting some equation. Here's your equation, assign some variable pi x. This alpha is some variable you're going to designate into your function. So you can, if you want to change it, you can change it later on. So you don't have to keep rewriting the function. You can just change the variable inside. So here we have a function Dirichlet boundary condition. We have the variable u is acting on, the two boundaries, and the function is being called upon. Also, if I'm going too fast, please stop me if you have any questions. So yeah, before we go to energy equation, does anybody have any questions about coupled variables or the functions? Nope. Okay. So energy equation, we're not going to get too much into any energy equation right now because when we go over talked about ZAPs. So here's our basic energy equation. Each part of these are divided into kernels. And we'll show you what those kernels look like in the input file when we go over the Zapdos presentation today. And this is just an assumption we're using where we're saying the energy is, instead of calculating the temperature. So auxiliary variables and kernels. So instead of calculating a variable directly, let's say defining it in our variables, what we can do is you can set it as an auxiliary variable. We'll go back to step 3 to calculate the electric field of the potential results. So you can apply your auxiliary systems to kernels, boundary conditions, material properties. You can also couple them to useful for reviewing things that you don't solve for, like velocity, or in this case, or our case, the electric field. There's 2 types. So you can either do the auxiliary variable over an element, or you can do the auxiliary variable over at a node. They're set up the same. What determines which is when you declare it inside the input file. So yeah, the element auxiliary variables compute the average value over an element. So yep, nodal, like I just said before, it's called, computes the variable at a node. It can only use nonlinear variables and other nodal auxiliary variables. Auxiliary variables have an old state just like nonlinear, so if you want to call back, you can do call back to old, which is previous step, time step, or you can do older, which is 2 time steps before. So when you put it, auxiliary variable kernels are different from kernels in that you have to put .c files. They would go under their separate file. They wouldn't go inside the kernels. It's the same thing with regular kernels, though. You do have to override variables and override the compute residual. Luckily, though, there is no Jacobian you need to solve for because you're not. They don't apply to the solution. They're just an extra variable that you want to account for. They're calculated from what Moose is trying to solve for. Like I just said earlier, there's no difference between nodal. Not exactly, no. Post-processing is its own subject. Yeah.
So when you're doing a post-processor, generally, so post-processors come out on the console screen, and you can say that you can tell them to be written to a CSV file. So they're like a global calculated value. So say you wanted the average temperature on a. In this case, this is something that is calculated based on your variables, the other variables in your system, or other values in your system that could vary across the domain. So you're calculating on a nodal by nodal or elemental by elemental basis. And so that can be displayed along with the data that's created when Moose solves for your solution variables, but this doesn't get solved for. So it's why you're not overriding compute QP residual because it doesn't contribute to your Jacobian or your calculation. You're just.
So just like variables, you'll have, when you operate them in the kernel, it's designated as U or grad U. They do still have quadrilateral points, and they do still have Q points. So just like you would do for a regular kernel, you can treat the variable similar in auxiliary kernel. But remember, it's not needed to solve the actual nonlinear and linear equations. Kernel, similar, we have a nodal one that only applies to. Oh, yes, go ahead. So if you're doing over an element, I believe it's interpolated based on their basis function, if I'm correct. If it's at a node, then no, you're calculating at the node itself. So it depends on which one you're using. Yeah, if you're using elements based off your basis function you're using.
And I will add to that. So if you're say you're in ParaView and you're viewing in ParaView, to interpolate it or across everything, the ParaView can actually allow you to convert point to cell data, and it interpolates it inside of ParaView. So if you wanted to view something a little bit differently and not just have it defined at the nodes for visualization purposes, you can do that outside of it. But in terms of the calculation, like it's letting you choose, and then you can convert it later if you need to.
Okay, so similar to what we did yesterday, our auxiliary kernel, you still have to designate the title. If you're inheriting from another auxiliary kernel, you need to include it. You need to add the parameters and any variables that are inside your auxiliary variable would be designated right here. Again, override compute variable value. Similar, a variable, you have to designate it, param, add required, whatever variable it's acting on. You have to compute whatever you're computing. In this case, it's the electric field, or what we need to call whatever acting upon. So in this case, it's electric field. So what we need is the gradient of our potential. Down here, we're actually computing the value, which again is simply just the gradient of our potential. We only have one active variable. We also have another auxiliary variable. We have a kernel section. Remember, the kernel section is only for the variables. We have a separate auxiliary kernel block for auxiliary variables. And note right here, just like with any normal couple variable, you designate the kernel or auxiliary kernel the variable is acting upon, and the couple yesterday. Problem setup is the same as yesterday. All we're doing is adding the coupled. All we're doing is calculating the electric field. So before I move on, let me actually run this code so we can get an idea what it looks like. Okay. Control the plus. Yeah. Can everyone see this?
Yeah, I'll dim the lights just a little bit.
Okay. Bigger? Good? So again, mesh, a variable. Might have skipped over this, but auxiliary variables, you can still call the family in order. And it's exactly the same input file as step 3. So let's run this. So if we go to CD, wherever your should have built this. Okay, I switched the order. That's what happened. There we go. Relatively quick to solve like before, because again, we're not actually changing any Jacobian. We're still just solving the potential. Just alongside that, we're going to calculate Yep, it's right here. Again, before, as we mentioned yesterday, it's bigger. So if you look at our voltage, calculating step 3, we get this kind of parabolic arc. And then if you want to calculate, again, the electric field is just the gradient. So if we take the gradient of this, what we expect is a straight line. About auxiliary kernels, couple variables, anything. Nope. Okay. Oh, view. Okay. Yeah. But unfortunately, because of time savers, we're going to skip this. And there's your example. We're also skipping interface kernels. I'll briefly go over that in Zapdos, because Zapdos does have capability of doing interface processors. So post-processors, again, as he mentioned, Casey mentioned before, they calculate, they can calculate an average over some element. They can be average velocity, surface power, deposition, max temperatures. Moose comes with some standard preconditioning that if you make an application, is already there in your application. But if you want to build off of those, you can always inherit value. In this case, we have a temperature. And we're just taking the average of our temperature by integrating it and dividing over our volume. So for post-processor, we can do reduce or aggregate calculations, as we mentioned before, on resulting in a single scalar value, linear, beginning of time step, or you can even customize it. So like if you have a RF discharge and you want to find the power in that one RF cycle, you can build a post-processor to do that. They can be restricted to particular blocks, subsections, nodal sections in your domain. Again, post-processor, similarly to auxiliary kernels, you can also do it on nodes. They just operate on each node. Can be restricted by one or more boundary IDs, and again, inherited from the nodal post-processor. But there are a little bit more. You can also do sides. These operate on the boundaries. You can just go with a generic post-processor and build upon that. So just like with kernels and auxiliary kernels, some initializing you have to do. Void initialization, clear or initialize your data structure before executing. Void execute, calling upon each dynamical entry for the type. If I'm not mistaken, this is more for parallelism and higher computing, correct? Yeah. Which we're not going to talk in too much. If you really want to know more, these two are more the experts. I don't deal with that too much. Void finalization, again, this you might need to use MPIs. Serves as an aggregate route and available in your limp mesh parallel.h file. What you will need, though, is the real get value. This will determine whatever your scalar variable is, where you're computing out of your post-processing. And create a custom data, i.e. you can include, create and compute a member variable inside your post-processor. You will need to ensure that the value is communicated properly. Just know that these functions are out there. Do you want me to go elaborate more on these, or let us go? Similarly with these is for parallelism. Just know that they're out there. And parallelism, we don't really need to worry about this, unique has the base function reference to the current type, so you can access the directory structure. It's all the information is there if you want to look at it, but again, we're not really looking at parallelism or element integration. Integrate over an element. Do element average variable as we saw in the beginning for that temperature example. Side. So if you apply your post-processor on a side, similar thing, you can integrate our average value. You can also calculate the error, the L. For instance, if you want the average flux on one side, you can inherit the side average value and override the integration and compute the flux for every quadrilateral point. For each element inside processor, you can use material properties and functions. By default, they output a table you'll see on your screen, but it can also be written by exe file as a global data. It got cut off. It is possible to set default values on post-processors. If you want to call upon a post-processor and any other Moose objects, such as a kernel. Similar to auxiliary variables, the default value and description. And exactly as any couple variables, auxiliary variables, you have to designate it. Additionally, users may supply real again, like with auxiliary variables or couple variables, auxiliary scalar value, so you don't have to compute it. This is great for, again, debugging. So over here, again, post-processors is a separate block. So this is dedicating to output the number of freedoms you have. In this particular case, they're calculating both the H1 error and the L2 error for our post-processors today, kernels, boundary conditions, such. And this is what you actually compute out on your screen. This is the time step, degrees of freedom, and your post-processing value. In this case, our H1 and L2 error.
So let's take a quick 5-minute break. We're going to switch over to my laptop and continue. We're actually just a little bit ahead of schedule, so I'm going to go ahead and